Here's a question with a surprisingly small answer. How big a solar farm would you need to power the entire United States? Not supplement it, not help with peak load, replace everything. Every power plant, every grid, all of it. The number is smaller than most people expect, and then the number stops being the problem. So let's take this completely seriously and find out what the actual problem is. The answer to the land question is about the size of one Nevada county. But let's be specific.
First, the electricity. The United States consumes about 4,000 terawatt-hours of electricity per year. That's the number we need to match. Not total energy, just electricity. Electricity is roughly 20% of total U.S. energy consumption, since most energy is used directly as heat or fuel. We're solving for the electrical grid, which is already the hardest part. 4,000 terawatt-hours. Let's build a solar farm to generate it. The best solar resource in the continental U.S. is in the Southwest, Nevada, Arizona, New Mexico. In these regions, a square kilometer of solar panels with a modern efficiency of about 22% generates roughly 400 gigawatt-hours of electricity per year under real-world conditions. That accounts for night, clouds, seasonal variation, and panel degradation. It's not a theoretical number, it's what you actually get. Divide 4,000 terawatt-hours by 400 gigawatt-hours per square kilometer, and you need about 10,000 square kilometers of solar panels. That's a square roughly 100 kilometers on each side. Nevada alone covers 286,000 square kilometers. Our solar farm fits inside Nevada about 28 times over. This is the number that surprises people. It is not a lot of land. It is less land than is currently used for coal mining in the United States. It is smaller than the Mojave Desert. It is, in the grand scheme of American geography, basically a rounding error. So the land problem is solved, and then everything else becomes the problem.
The first everything else is storage. Solar panels generate electricity when the sun shines. The U.S. needs electricity when the sun doesn't shine, at night, in winter, during cloudy weeks in the Pacific Northwest. The gap between when solar generates power and when people need it is not a small engineering problem. It is arguably the central unsolved problem of the entire energy transition. To cover a typical overnight gap for the U.S. grid, you need roughly 12 terawatt-hours of storage. The entire global battery manufacturing capacity in 2023 produced about 700 gigawatt-hours of batteries across all uses, including electric vehicles. To build 12 terawatt-hours of storage, you need to run the entire global battery industry dedicated exclusively to this project for about 17 years. That's for one night. A cloudy week in winter requires substantially more.
The second everything else is the grid itself. The U.S. electrical grid is not one grid. It is three largely separate grids: the Eastern Interconnection, the Western Interconnection, and Texas, which has its own grid for reasons that are historically complicated and occasionally catastrophic. Moving electricity from a solar farm in Nevada to a city in New England requires transmission infrastructure that largely does not exist. Building sufficient transmission lines to connect a Southwest solar farm to the entire country would require roughly 100,000 kilometers of new high-voltage transmission lines. The U.S. currently builds about 1,000 kilometers of new transmission per year. At that rate, the transmission alone takes a century. You could accelerate the build rate, engineers have, but permitting, land rights, and regulatory approval for transmission lines in the U.S. currently takes an average of 10 years per project. The solar panels themselves are the easy part.
The third everything else is cost. 10,000 square kilometers of solar panels at current installed cost runs to approximately $3 trillion. The transmission infrastructure adds another $2 to $4 trillion. The storage adds somewhere between $5 and $20 trillion depending on the technology. Total system cost lands somewhere between $10 and $27 trillion, roughly 1 to 2 times the entire annual U.S. GDP. This is not obviously unaffordable over a long enough time horizon. The U.S. spends about $400 billion on energy infrastructure annually. Spread the cost over 30 years, and it's roughly double current spending. Ambitious, but not physically impossible. The panels themselves are fine, by the way. Modern solar panels work exactly as advertised, last 25 to 30 years, and get cheaper every year. We've completely mastered turning sunlight into electricity. It's the storage, the grid, the permitting, the transmission, the financing, the politics, and the 17 years of global battery production that keep getting in the way.